We will now cover the conceptual design of a distillation column. In a previous topic, the ternary map is used to check if the mixture can be separated by simple distillation or how many columns are needed to reach the separation goal. However, for each column, engineers also must further answer questions such as how many stages are required, or what is a good feed location and reflux ratio. In Aspen Plus, the conceptual design block named Concept can be used for these designs. The conceptual design block is available in the column section of the model library. The concept block requires 3 specifications to be defined: the outlet composition or recovery, the reflux or reboil ratio, and the operating pressure. One main feature of the conceptual design block uses an interactive ternary diagram. The diagram shows the rectifying and stripping sections of the column. Adjusting inputs from the ternary diagram will interactively generate corresponding column design specifications, such as feed stage location and number of stages needed for the desired separation. Let's use Concept for the conceptual design, beginning with a separation sequence determined by using ternary maps in Aspen distillation synthesis. Here we have a pressure swing distillation sequence leveraging 2 columns to separate a feed containing 65% acetone, 20% MEK, and 15% water into a stream containing 97.9% acetone, 0.2% MEK, and 0.19% water at 99% molar recovery of acetone. From the ternary map and defined separation objective, we can obtain these requirements for both distillation columns. In the first column, we can read from the ternary diagram that the distillate contains 78% acetone and the bottoms contain 99% MEK. In the second column, 97.9% acetone and 1.9% water at distillate are the separation objectives. The recovery of 2 columns is set such that the total recovery is 99%, which is the product of 99.9% and 99.1%. These design specs give us a starting point for determining a conceptual design. With this in mind, let's move to the simulation environment to use the conceptual design block for designing these 2 columns. Let's do the column designs one by one. Add a concept block to the model. Connect the feed, bottoms, and distillate streams. Double-click on the feed stream to input the stream information: 30 Celsius, 10 bar for pressure, since the feed pressure must be greater than the operating pressure of 6 bar, and a total flow rate of 100 kmol per hour, or about 81 cubic meters per hour, with a composition of 15% water, 20% MEK, and 65% acetone. In the concept block, select key components as water, MEK, and acetone. Set the composition of acetone in the distillate stream as 78% with recovery of 99.9%, and composition of MEK in the bottom stream as 99%. For the specification, let's set the reflux ratio to 2. The operating pressure is 6 bar. Click on the Interactive Design button. It is a valid design with 49.4 total stages. Can we operate at lower pressure to reach the desired purity? Enter a pressure of 5 bar and click on Recalculate. The rectifying and stripping section lines do not intersect, so the design is not feasible. This explains why we selected 6 bar as the operating pressure for the first column. Click Reset to return to the original settings. The interactive design can also determine the minimum reflux ratio and minimum number of stages. Let's lower the reflux ratio until the solution is infeasible to get the minimum reflux ratio of 1.57, corresponding to 106.1 stages. A detailed approach would be used in practice to determine the best design based on cost trade-offs. Here, a proxy would be that the best design would trade off between low reflux ratio and low number of stages. We will use a sensitivity study to determine this. Create a sensitivity analysis. In the vary sheet, let's copy the reflux ratio as a manipulated variable. Input a reflux ratio range from 1.57 to 6 across 20 points. In the Define tab, we need to copy the number of column stages as a sample variable. Go to the Tabulate sheet, click Filled Variables. Run the analysis and plot the results. We can see nearly a flat platform formed when the reflux ratio is around 5.5, where we find the minimum number of stages. Run the simulation with this optimized reflux ratio. The results of the concept block can be found under the Results tab. In the Material Balance tab, we can see that our design requirements, such as acetone composition, recovery, and composition of MEK, are satisfied. In the Design tab, we can see the total column stages, phase stage, reflux ratio, and other detailed information. In the Liquid and Vapor profile, we can see the temperature and composition of phase across the stages. Now let's design the second column. Add a second concept block and connect the streams. Input composition of acetone in distillate stream as 0.979 with recovery of 0.991 and composition of water as 0.019. For the specification input, let's try reflux ratio as 2. Operating pressure is 0.7 bar. Click Interactive Design. It is a valid design. Similarly, we can play with input variables to find the best design, but we will leave that for you. Now that we have the number of theoretical stages and the reflux ratio of both columns, we need to use a rigorous column model RADFRAC to do further analysis on the system. In the next topic, we will convert conceptual blocks into RADFRAC.